Okay, we can launch into questions and answers now, or this is our general discussion time too. It's, if you have questions for Justin or whatever you want to say is fair game.
This is Andy. I've got a question regarding the channels on the moon. Justin said they were melting the rock below. What would be the composition of that rock below? Would that be the amethyrsite type composition that we see in the highlands?
So the moon has been pulverized a lot, and so you can see here where there is some highlands material, but you can see here we're sitting on the Mare Plains, so you can see here it goes around some of the highland stuff. So you're melting through both the Mare, the previous volcanism of the Mare, plus whatever's underneath that of the highlands material as well. So the original crust in some cases was remelted. In some cases it was just remelting previous lava flows.
And do you have a guesstimate of how old that flow might be?
I don't work on the moon that much, so no, I don't. These are, most of the volcanism that happened on the moon happened shortly after the crust formed. So these are very, very old, greater than around 4 billion year old lava flows.
Thank you.
Refer to the previous seminar by Julie Stopar, your colleague. That was her main focus was at the moon.
Oh, okay. Oh,
but she didn't do all about volcanoes though, so this was good. By the way, that image that you showed of the diagram from the Earth with the heat coming out to the surface by these blobs coming up. Yeah, that's exactly it. That I can't help but say that reminds me of the lava lamp. And,
it's actually very similar to the lava lamp. You are absolutely correct.
that dates me, of course, but
no, I had a lava lamp when I was a kid. But yes, it's the same thing where the core was your light bulb, and as it heated the mantle or that plasticky fluid stuff, it rose up. And in the case of volcanism, it got so hot to melt and that erupted to the surface.
I do have a question actually about, actually I have a few questions, but, and by the way, on the display here, under me, it says Pacific Planetarium, something or other. I'm actually Alan Gould. I didn't introduce myself.
Planetarium?
Yeah. Well, I think I'm logged in as the president, but Carl is actually the president. Anyway, my question is, it's about you were saying when we were at Venus that the radar images are not the same as the visual imaging. And you mentioned that the features can represent porosity, density, elevation. Could you go over that once again, and what were the things that it could be?
So the brightness or darkness of a radar image is dependent on the density of the material, first and foremost, which goes with porosity, chemistry, physical structure, so a large solid piece versus smaller broken up pieces, as well to some extent as elevation. And so you can see here, a lot of this area down here is the same elevation, but this is a younger lava flow, and so it's brighter than what's sitting around it, which tells us that this is altered, whereas this is younger and fresher.
Because it's more, it's harder, so it reflects the radar more easily.
It's
less porous.
This is harder, and the mineralogy is different as it alters it. Venus has such high sulfur and CO2 that this likely has the irons being changed out to sulfides or carbonates. And so we're seeing a change in the physical state of this going to this. If you go to Hawaii, this would be like walking on the fresh lava flow. And then as you go to the older ones, you can start seeing the rock starting to get a little rounded, some other coatings coming in, things like that. And that's what we're seeing as we go from here to there.
I had a follow-up to my question about how deep that probe was going. 2 meters down doesn't seem like it's going to be able to detect much, especially concerning volcanic activity or anything. It'd be more
Yes.
just the surface. And yeah, how does that work, and how is that useful?
So it is going to get crustal heat flow and not volcanic heat flow. We're not sitting on a young lava flow to tell us how hot the lava is.
Right.
This is going to get us crustal heat flow, which tells us about how the entire planet is cooling. And if the planet's too cold, then there can't be heat coming from the interior. If the crustal heat flow is high enough, then we can model back based on how thick the crust is, how big the planet is, and things like that to tell how much heat would be in the interior as well. And then we could say that there could be volcanic activity or not. And so it's not a direct measure of the temperature of a lava or the temperature of volcanic activity, but it tells us about the temperature of the whole planet, which then we can get back to what would be the temperature of the interior.
Oh, thank you.
Along the same lines as a question about the heat flow probe drill, this is more of like an engineering question. When I saw the picture of the heat flow probe instrument, it looks like a box. It reminds me of a magazine loading thing, where the drill, there would be a certain depth of drill, and then another piece would be loaded in from the side to go deeper. Is that kind of how it works, or am I mistaken in that? It's almost like a gun or I don't know how drilling is done, actually. That's what my question is do pieces get loaded into that vertical part?
If I'm not mistaken, this is a self sort of pushing down structure with a tether on it, and on the tether going up has more or less thermometers that can then measure the temperature. And so this is the piece that moves and articulating drilling down through the crust. But
that's not 2 meters, though. I mean, that thing is not 2 meters. Is it telescoping or something?
No, it's attached through a cable.
Oh, it's like wound up.
Yeah.
Okay.
Spring, huh?
Okay.
Again,
I had not pictured that.
I'm not an engineer, so that's based on what I've been told.
Yeah. Well, you know more than I do.
When NASA came here, they brought a demo of that self-hammering probe, and it was cool to see it working, sort of. Although they weren't drilling down through anything, they just showed it sort of hammering.
Interesting. Let's see. While we're on Mars, that Tharsis Tholus, you said, had an impact crater on the flank. Would you mind?
It actually has a couple here. So there's 2 over here, 1 over here, a couple little ones there.
Yeah. So just to refresh our memory, those of us who learned this long ago, how do you tell the difference between an impact crater and a volcanic?
So in this case, you can see a nice circular structure, and then in the center, you can see a slight uplift or the rebound structure of the interior. And so that would give away that this is a simple crater.
That's a dead giveaway. Yeah.
Yeah. Here you can see. Was there a question?
I think Vince has some background noise there.
Okay, no, that's fine. Here you can see that we've got nested craters, so that again gives away that it's a volcanic structure. We don't typically get something like this with impacts. And the same thing here, you've got a very circular high rim, and then we should see an ejecta blanket that goes out in all directions. And I'm not seeing it here, but if we had higher resolution images, you would see it. And that gives away that they're impact and not volcanic features. But if you go back in history, that was actually the big debate for the moon, was whether everything we were seeing was impact or volcanic. And it swung back and forth many times, with everything being impact and everything being volcanic. And it wasn't until they found shock quartz out at Meteor Crater and we figured out how to find impact craters, that we started to realize that almost all of what we were seeing on the moon was impact, and just these isolated things I showed you were volcanic.
You know, those comparative, images that compare features on Earth and Mars, those are really interesting and really valuable. And I was one of the things I was noticing was actually this whole idea of a knowledgeable scientist explaining what we're seeing in these images reminds me of, there's a movement in the planetarium world called data to dome. And there's all kinds of different data sets, and these images are one type of data set. But the interpretation of the data, in my estimation, is one of the most important things for us as planetarians, to be able to explain to people what it is. If we don't know what it is, it's guys like you who tell us what it is. Like, for instance, that picture of the lunar rover in that rill, or the lava flow on Mars, I think I had seen that picture, but I thought that I had not looked at it carefully enough to see that. I thought that was the edge of a crater.
No,
but if you look carefully, it's clearly a meandering kind of lava flow.
Yeah, it's Hadley Ryle.
Yeah. But so these kinds of interpretation things are really valuable.
I actually have worked with Christine Schupla here in our portable dome, doing some presentations to the public. And so we sort of tag team. She does the stars and the physics and astronomy, and I do the planetary science, which is kind of fun doing that, where I can get up there and talk about the volcanoes and project one on the dome, and she can talk about the stars.
I guess I have one other question that is nagging at me. I found it fascinating, the comparative slopes of things, and the general, the general idea that a shield volcano has a much smaller slope than a what do you call the other one?
Composite or strato.
Stratovolcano. But a question that occurred to me is that, does the surface gravity of the planet have any effect on the slope of a volcano?
The surface gravity will have minimal impact. It's the thickness of the atmosphere and the temperature at the surface that actually have a larger effect. And so this is probably why Venus has these very, very shallow slope volcanoes, is we have a much thicker, heavier atmosphere, and it's a lot hotter. So instead of building up, the magma wants to go out. Whereas Mars is colder, although these are old, but thinner, colder atmosphere, and so we're growing up instead of out. Gravity will have a little bit of an effect on how thick the lava flow wants to be, but temperature and atmospheric density actually have the two larger effects.
So I guess that, you mentioned Io earlier, and I know that that's not the inner solar system, the subject, but that would have very low gravity. And
so here's Io. We've actually seen, it's the only other planetary body where we've seen evidence for active volcanism. Here's a gas plume, and then we've got surface changes here where we had lava lake overturning. This is Loki, which is a lava lake. But talking about surface height, so this is Ray Patera. It's 450 kilometers in diameter. It's less than a kilometer high. And if we compare it, it is way down here.
Oh, oh really low slope, huh?
Really low slope. It looks a lot more like Venus, but even lower slope than what we see on Venus. And the reason for this is probably the heat, the temperature of eruption is probably hotter than we see on Venus. And so we've got runnier magmas. And we've got so much sulfur in the magma that it's probably changing the physical properties. So for the case of Venus, it's probably the atmosphere and temperature difference. Here it's because of the difference in chemistry of the lava. It's probably a couple hundred degrees hotter than the hottest lava in Hawaii.
You know, and while we've expanded the discussion, since we do have time, what about volcanism on Mercury?
Okay, so Mercury, up until a few years ago, we didn't have imaging of the surface, but we do now from MESSENGER. And this is a false coloring image, and you can see the black areas are showing volcanoes. If we zoom in, you can see this bright spot here. These are craters, but here we've got a small volcano. So this is 50 kilometers across. Nice large caldera or cratered, nested crater system here. And then you can see here we've got lava flows going across the center, and this is an old impact crater where the lava actually came in and filled over the lava. And so this is telling us that these are geologically relatively young. We don't have a good age for them because we don't have samples of Mercury to date to compare to like we do the Moon or Mars. But it tells us that this had to happen first and then it filled in with lava here.
You know, that actually, if you'd have shown me that picture without saying anything about it, I would say it looked like a pancake.
It does look like a pancake. It's not. It is an old impact crater that was then filled in. You can see the edge of the lava flow, or some of the structure of the lava flow, as it came in and flooded over the lava, or the old crater. Mercury is weird. The chemistry of the surface is so different than any other planet that we actually can't really use terrestrial analogs when we go to Venus. And so we're trying to figure out what these are and what type of volcanism and how young is young volcanism on Mercury. So that's what we have for Mercury at the moment.
Yeah. You know, looking at that picture again, I would not have guessed that to be a crater, mainly because if you just compare it with other craters, the relief is not apparent, and it looks like a plateau. I mean, like I said, it looks like a pancake.
That's because it was a crater and has now been completely filled in by lava. And as the lava cooled, it did make a slight plateau on the outside. Okay. So what you're seeing is correct. And that's why it's not in indent anymore. It's where the magma sort of filled it in.
Yeah, this is something that people have trouble with interpreting the shadows. You know, where is the sun in a particular picture and how their shadows form, because what looks like a crater can look like something else.
Yeah, you can see down here, we have a crater where it's sunken in, and another one up here where these are craters. This is a filled in crater where the lava completely capped it off. Yeah. So you can see the difference between sort of that flat surface here and an impact structure.
Yeah, that's fascinating.
And I'm curious, that line coming out of the pancake at 1 o'clock and going up, would that be lava flowing out of the plateau onto those?
This feature here?
Yeah.
This is presumably from how the lava cooled. We don't get nice flat surfaces. If you've been to Hawaii, an old lava flow won't be nice and perfectly flat anymore. It has structure to the top, and this is probably what we're seeing is structure from the lava as it flowed over other things.
I've got another question going back to Io. So you were saying the magma was a lot hotter, but what about the atmospheric condition or the surface conditions being a lot cooler on Io? How would that affect the magma?
So cooler surface conditions typically make the magma cool off quicker. However, because Io is the magma is so hot, it can make a surface crust on the magma and then still let the magma flow underneath it. We see this in Hawaii where you'll get the nice crust and the magma coming under and then may pop out again as it comes down. You can see here, this is Loki Patera, and you can see the structure here, and there's some island in the middle. This is what's interpreted to be a lava lake because based on spectral images, you can back out temperature from them. This is February 2000 and October 1999, and these are temperature contours, and they've changed through time, saying that there was a cold crust on this lava lake, and then as new magma came in and broke the crust, it broke it up, and we have a new piece or new magma area shown here, and then that cooled off, and now it's over here. And so this gives us an idea of what's going on in the magma of Io, but we don't have actual temperatures, and we don't have direct chemistry of these. Everything's based on surface morphology estimates and comparisons with the Earth.
Yeah, and I've heard some kind of interesting speculation that there could be conditions, if the hot lava is heating up water ice, you could have conditions where you have liquid water on Io, and who knows, could there be some sort of life form that could take shape in there.
Yeah, I think if we were going to go to the outer solar system and look for life, I think Europa or Enceladus would be our better bet to jump to than Io. But yes, I have heard about sort of hydrothermal systems on even Io potentially being habitable.
Why not go to all three?
Sure.
Well, we could afford to do that if we don't do manned missions. If we don't do a manned mission to Mars, maybe we could afford some of that other stuff. It's always a trade-off. I'm not advocating anything in particular, but I'm mentioning the lava tubes on Earth. I know that there's like lava tubes where the crust forms and the lava flows through it. Is there anything like that on Io? Like actual tubes?
We have not seen lava tubes on Io. We have seen them on the Moon and Mars.
I'm
going to have to leave. My battery's about to die here. So excellent, though. Thank you so much. And see everybody soon.
Yeah.
Thanks.
Actually, your battery is dying at about the 1 hour mark. So
timed it pretty good, I guess.
we should start wrapping up. Are there any last questions? I
have to wrap up too. I'm actually a stone's throw from Carl's boyhood home here. And yeah, I've got to take off too. So, but thank you. Very, very fascinating.
Okay.
Good combination of talks with the moon last month and then the inner solar system this month. Yeah,
this has been the Lunar and Planetary Institute series.
Not a bad thing.
Yeah. Well, anyway, yeah. Thank you, Justin. This has been a really interesting experience for all of us. And
thank you.
One more round of applause from everybody who's still here. Okay.
Thanks.
So this is signing off. We're not going to have a seminar in December. We're going to start up again in 2019, and we're going to be having a collaboration with GLPA, Great Lakes Planetarium Association. They're going to help organize these and host them, and So we'll be a joint organization then. Okay, thanks again, Justin. Signing off.
All right. Bye all.